reaction, House synthesis. This method was developed around 1970 and is a much better method than Wood's reaction for preparing alkanes containing higher number of carbon atoms than the reactant taken. It consists of reaction between alkyl halide and a lithium dialkyl copper. For example, alkyl halide plus lithium dialkyl copper gives alkane plus RCU plus LIX. For example, N-butyl bromide plus lithium dimethyl copper gives N-pentane methyl copper plus LiBr. Lithium dialkyl copper required in this reaction is itself prepared from alkyl halide as illustrated below. Rx plus 2 alkyl in presence of dry ether gives RLi plus LiX. 2RLi plus CuX gives R2CuLi plus LiX. To obtain yield of alkanes, alkyl halide used is generally a primary alkyl halide, while the alkyl groups in lithium dialkyl copper may be primary, secondary, or tertiary. An important feature of this reaction is that it can be used for preparing all types of alkane, whether symmetrical or unsymmetrical, whether straight chain or branched chain. Mechanism. In the beginning, the alkyl group of alkyl lithium displaces halogen from copper halide to form alkyl copper. RLi with CuX gives alkyl copper plus LiX. Alkyl copper react further with alkyl lithium to form lithium dialkyl cuprate. LiR plus CuR gives R2Cu negative Li positive. Alkyl halide then undergoes nucleophilic attack by dialkyl cuprate anion to generate an unstable intermediate which decomposes to give the final product. R2Cu negative plus R-X gives R2CuR double dash X negative gives RR dash plus RCu plus X negative. Called electrolysis reaction. In this reaction, concentrated aqueous solution of sodium or potassium salt of monocarboxylic acid is subjected to electrolysis to get alkanes. Now RCOO Na plus 2H2O in presence of electrolysis gives alkanes plus 2NaOH plus H2. The reaction takes place as follows. 2RCOONA ionization in equilibrium 2RCOO negative plus 2Na positive. 2H2O ionization and in equilibrium 2H positive plus 2OH negative. 2RCOO negative minus 2E negatives gives 2RCOO gives RR plus 2CO2 at anode. 2H positive plus 2E negatives gives H2 at the cathode. The discharge potential of H positive ions is lower than that of Na positive ion. Therefore, H positive ions are discharged at the cathode, liberating H2, while Na positive ion remain in solution. For example, 2CH3COONA gives in equilibrium gives CH3COO negative plus 2Na positive. 2CH3COO negatives minus 2 electron negatives gives 2CH3COO gives ethane plus 2CO2 at the anode. 2H positive plus 2 electron negatives gives H2 at the cathode. This is a good method for preparing ethane and higher alkanes having even number of carbon atoms. Methanes cannot be prepared by this method. Decarboxylation of monocarboxylic acid when heated with soda lime, NaOH plus CaO, sodium salts of monocarboxylic or fatty acid undergoes decarboxylation to form alkanes. The reaction involves the elimination of carbon dioxide from carboxylic acid. Active component of soda lime in this reaction is sodium hydroxide, but it is not employed as such because it melts on heating and it's deliquescent as well. Sodium salt of fatty acid plus sodium hydroxide in presence of CaO gives alkanes plus Na2CO3. Example: CH3COONA plus NaOH gives methane plus Na2CO3. Oakwood and co-workers have shown that the reactions proceed according to the above equation only in case of sodium acetate. In case of higher members, various side products are also obtained. Thus, in the case of sodium propionate, the reactions gives methane, hydrogen, and certain unsaturated hydrocarbons also in addition to ethane. It may be pointed out that the alkanes are also formed during some other chemical reactions, but these reactants are not employed for the actual preparation of alkanes either because of the poor yield of the desired products or some other drawbacks. Preparation of methane. Besides methods numbers 2, 4, and 6 described above, methane can also be prepared conveniently by dropping water over aluminium carbide. Aluminium carbide plus 12H2O gives 4Al bracket OH bracket 3 plus 3CH4. The gas obtained by this method is generally contaminated with hydrogen and acetylene. Preparation of ethanes. Although ethane can be prepared by any of the general method of preparation, it is generally prepared in the laboratory by the reduction of ethyl iodide or ethyl bromide with the nascent oxygen nascent hydrogen produced by the action of zinc copper couple on ethyl alcohol. For example, C2H5OH plus zinc in presence of copper gives zinc ethoxide plus 2H. Now, for example, ethyl iodide plus 2H gives ethane plus Hi. Physical properties of alkanes. Physical state. The lower members of alkanes containing up to 4 hydrocarbons are colorless gases. The higher normal alkanes having 5 to 17 carbon atoms are colorless liquid, and beyond that they are colorless solids at room temperatures. Boiling points. The boiling point of an alkanes increases regularly with the increasing number of carbon atoms. There is an increase of about 20 to 30 degrees for each carbon atom added to the chain, except in the first few cases where the increase is much more. This can be explained in terms of intermolecular force of attractions. Alkanes are non-polar compounds having weak van der Waals forces of attractions between their molecules. These forces act along the surface of molecules and their magnitude increase with increase in surface area. As the molecular size of alkanes increase, the surface area and strength of van der Waals forces also increase. As a result, the boiling point also increases. Amongst the isomeric alkanes, there are small differences in the boiling point of various isomers. The branched chain isomers having invariably lesser boiling point than the normal compound, and in greater the branching, the lower is the boiling point of branched isomer. For instance, the boiling point of N-pentane, isopentane, and neopentenes are 309, 301 and 282.5 Kelvin respectively. This is due to the fact that branched isomers are more compact, they have lesser surface area than their normal counterparts. Due to lesser surface area of such molecules, the van der Waals forces of attractions operating Due to lesser surface area of such molecules, the van der Waals forces of attractions operating between them are comparatively weaker. As such, lesser energy is needed to overcome this force for the boiling to take place, and therefore the boiling points are lower. Melting points. The melting points of alkanes do not show a very smooth gradation with the increase in molecular molecular size. For instance, let us consider the melting point of N-propane to N-octane. It may be seen that increasing in melting point is much more in moving from an alkane having odd number of carbon atoms to the higher alkanes than in moving from an alkanes having even number of carbon atoms to the higher atoms. This is essentially because the intermolecular forces in a crystal depend upon only upon the size of the molecule but also depend upon how well the molecule fits in the crystal's lattice. It has been already made clear that the carbons in alkenes form zigzag type of chain rather than straight chains. Now in an alkanes containing an even number of hydrocarbon atoms, the terminal methyl group lie on the opposite side of the zigzag chain. On the other hand, in case of N alkanes having odd number of carbon atoms, the terminal methyl groups lie on the same side of the chain is shown below. It appears that the alkanes having an odd number of carbon atoms do not fit in so closely together in the crystal structure as the alkanes having an even number of carbon atoms. As a result, the energy required to break the crystal structure and thus melt the alkane in lesser in case of alkanes having odd number of carbon atoms. That is why they have lesser than expected melting points as shown only by slight increase in melting point, moving from an even number alkanes to the higher odd number alkanes. Specific gravity. The specific gravity of alkanes also increase with increasing molecular weight but become constant at about 0.8. This implies that all alkanes are lighter than water. Solubility. Due to nearly same electronegativities of carbon and hydrogen atom present in them and the symmetrical shape of their molecules, alkanes are non-polar in character. As such, they are insoluble in polar solvents such as water but dissolve freely in non-polar solvents such as ether. The solubility decreases with the increase in molecular weights.